Now we've reviewed the idea of sequences in general, and then more particularly arithmetic sequences and geometric sequences. And next we're going to consider the idea, what if instead of just listing out terms in a sequence, we then added together all those terms? That would give us the idea of a sum. And if our sequence is infinite and we add all those terms up together, that's what would give us an infinite sum. And in this case, we call adding up all the terms of a sequence a series. Now, one of the ways we represent series, since we're summing all the terms, is something called summation notation. The first in terms of a series, remember as you're learning the new word series, think about it, I've got a sequence and I'm just adding up all the terms, is expressed in summation notation by, here we recognize our term, this is the kth term in the series or the sequence. This is a sigma, which represents the summing up. And then it says you start when k is 1. So in this case, we'd start at the first term. And then what happens with the summation notation is k takes on all values. So k is 1. And then next you go to the next integer 2. Then next you go to 3. And you continue this until you get to whatever n is, the value at the top of the sequence. So this is describing for us the idea of repeated addition, starting at the first term and adding all the way up to the nth term. 1 is what's called the lower index of summation. This is called the upper index of summation. Now let's see this in a particular example. Here we've got the sum from k equal to 3 all the way up through all the integers until we get to 7. What are we summing up? The pattern k squared. So we're going to start with k taking on the value 3, that would be 3 squared. The sum means you keep adding. So we've taken care of k equals 3. Next we go to k equals 4. So we say 4 squared. We add. Next we go to k equals 5. That would be 5 squared. We add because it's the sum. Next we go to k equals 6. 6 squared. Next we go to k equals 7. That'd be 7 squared, and the reason we stop at 7 is because that was the upper limit of the sum. We don't go past that value. Now each of these can be simplified. This is going to be equal to 9 plus 16 plus 25 plus 36 plus 49, adding all that together, and we would get 135 as our answer. So the value of this sum is 135. And we recognize this term is what sets the pattern of what do you do with the k values. You square them. So starting at 3, we square 3. Then we square 4 and add it. We square 5 and add it. We square 6 and add it. We square 7 and add it. We stopped at 7 because that's our upper limit of the sum. So once we get used to the different pieces of the sum, we'll be able to evaluate any different sum that we're given. The starting point of the k values, the stopping point of the k values, and the expression that you use for that k. Now, earlier in the class we learned about an arithmetic sequence. And what an arithmetic series is it's just adding up all the terms and that's what would give you an arithmetic series. So think sequence is just a list of numbers related by some pattern. A series is the idea of adding up all of those numbers. So we know what an arithmetic sequence is, and now we know what an arithmetic series is. Now, since arithmetic sequences are filled with such a pattern, it happens to be that whenever you add up all those values, there's still a pattern evident. So if we wanted to find the sum adding up the first in terms of an arithmetic sequence, it would be exactly this formula. Now, generally, this capital S subscript n is the partial sum, and the reason we call it a partial sum is we're only summing up the first n terms. Now, for an arithmetic sequence, this is not for anything, only for arithmetic sequences. It is the term that you're summing up to n times the first term plus the a sub n term, all divided by 2. So this is a very helpful formula, but we know to only apply it whenever what we're summing up is an arithmetic sequence. So here we're asked find the sum of each of these arithmetic series. That tells us that each of these 5, 8, 11, 14, 17, 20, 23, 26, 29, 32, they would form an arithmetic series. And one way we could do this is we could just add up all of these values. Let's do that quickly in our calculator. And we would get 185. And this works if we're not adding up too many things. But we could imagine if we were adding a lot of terms, we would want to have a faster way to do this, which is why our above formula is helpful. Now, what do we need to make the above formula work? We need to know the first term and the last term, which we have. First term is 5, last term is 32. But we also have to know what is the order of the last term. What term is it in the sequence? Now, in this case, we could count that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here a sub 10 is 32, a sub 1 is 5. So the partial sum of the first 10 terms of this arithmetic sequence is going to be equal to 10 times 5 plus 32, all divided by 2. 10 times 37, all divided by 2, that's 370. When we divide that by 2, we would indeed get 185. So how would you use this formula? First, you need to realize that the terms that you're adding together come from an arithmetic sequence where each term is a common difference of the other. In this case, we were told we were dealing with the arithmetic series, so that was given to us. Then you need to know what's the first term that you're adding to the last term, add those together. And then you need to know the order of this last term because that's what you're going to multiply on the outside. So we had to count and see that this is the 10th term. Now our next case, we still know it's an arithmetic series, but in this case we're dealing with 20 as the first term, the second term is 15, the third term is 10, and then we've got this plus dot dot dot. That means the pattern continues until after you follow that pattern, eventually you'd get to negative 50. So in this case, our strategy of just adding them all up doesn't work because we don't have all the values written out in front of us. I also can't count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to find this is the 10th term because that's not correct in this case. This is 1, 2, 3, but since the dot 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 means things are missing, I can't say this is the 4th term. So you've got a few options. You could just list out all the values. What's the pattern? We seem to be subtracting 5, so next would come 5, then 0, then negative 5. You could list out all the values and add them, but I think that's going to be a bit lengthy. So what do we need to know for the formula? We need to know S sub, we don't know what this is yet, but it's equal to whatever order that is in the sequence times the first term plus the last term divided by 2. So recognize that our formula will be complete if we could only know how far along we are. Now we know a few things about this. This is an arithmetic sequence added together, and we know arithmetic sequences follow this general principle. And we know the common difference in this case is negative 5. We know the first term is 20. And we know that we've got some nth term that's equal to negative 50, and we would like to know what n is. So let's substitute all of these into the formula and we'll be able to solve for n. Negative 50 is the nth term, and it's equal to the first term of 20 plus whatever n is minus 1 times our common difference of negative 5. We now see I have an equation in one variable where I can solve for n, and once I get in, that's what goes into the formula, and we're going to be done with the problem. I just needed to know what term is this in the sequence. So I'm going to subtract a 20 from both sides, and we would get negative 70 equals negative 5 times n minus 1. Now let's divide both sides by negative 5. And that would give us 14. Now this is equal to n minus 1, so we have to add 1 to both sides to get n is equal to 15. So negative 50 is the 15th term. Now that we know the 15th term, all we have to do is plug 15 into our formula, and we'll find the sum of this entire value, or the value of this sum. So the sum, the partial sum of the first 15 terms is equal to 15 times the first term plus the last term divided by 2. Now that would simplify to 15 times negative 30, all divided by 2, which is negative 225. Now do remember that this partial sum formula can only be used if you're dealing with arithmetic sequences. You would not want to apply this in a different case because it would not give you the correct answer. Now let's translate this next problem. This is the sum of the formula 3k minus 8, where k takes on the values between 1 and 12 that are integers. So at first, we could write out the first term when k is 1, that's 3, times 1 minus 8. And all of this together happens when k equals 1. And then you add, now k is equal to 2, so that would be 3 times 2 minus 8, plus, and we're going to continue this until we get to k equals 3. Now I think we can see that this would be a somewhat lengthy process. And definitely if we're patient, we could deal with this piece at a time. Just to get some intuition, let's write out the first few terms. 3 minus 8 is a negative 5. Now 3 times 2 is 6 minus 8. 6 minus 8 is a negative 2. 3 times 3 is 9. Minus 8 is a positive 1. If I was to find the fourth term, that would be 3 times 4 is 12, minus 8 is 4. And as we're looking at these terms, our final one is 3 times 12 is 36, minus 8, and that should give us 28. Now notice I'm not writing out all these middle terms. I'm just writing out the first few to try to get a sense of a possible pattern. And what I've noticed is, at least in the first 3 terms, do you see I added 3 to get from negative 5 to negative 2. I added another 3 to get to a positive 1. I added another 3 to get to 4. This is an arithmetic sequence in disguise, where our first term is negative 5, and our common difference is equal to positive 3. And indeed, if we write out the formula, the nth term is the first term plus n minus 1 times the common difference. And the only difference here is they've distributed this and combined like terms to get a more simplified looking formula. For instance, negative 5 plus 3n minus 3, that would combine to give us negative 8 plus 3n. And then the only difference here is they're using the variable k instead of n, but that's just a labeling, so I could equivalently call these a sub k's as well. Now, how would you recognize that the sum you're looking at is really an arithmetic sequence? Whenever the sum appears to be a linear equation, 3x minus 8 we know is a straight line. That's the very idea of an arithmetic sequence. So if you're looking at the sum where the inside is a straight line, that's an arithmetic sequence in disguise. You can identify the first term, write out a few terms to figure out what the common difference is, and then the great thing about arithmetic sequence is we know the partial sum of the first n terms is equal to the n, the term that you're at, times the first term plus the last term that we're looking at, all divided by 2. Now I know the first term, negative 5. I know the last term, 28. I just needed to know what n is, but do we see that it's the 12th term? That's when we plug in k equals 12, so therefore it's the 12th term. So since we've recognized this as an arithmetic sequence, we don't have to write out all the terms, simplify each term, and then add them together. We can use this helpful formula. So our partial sum of the first 12 pieces of this arithmetic sequence is equal to 12 times the value of the first term plus the value of the last term we're considering, all divided by 2. Now we're going to simplify that. That's 12 times negative 23, or sorry, positive 23, all divided by 2. We can evaluate this in our calculator. That would be 138. So if we write out all of these terms from k equals 1 all the way up to k equals 12, add them together, we would get 138 as the value of that sum. So let's recap this problem. It was shortened because we wrote out the first few terms, we simplified them so we could see what was going on, and we said, hey, this is an arithmetic sequence between the terms, where the first term is 5, the common difference is 3, and I verified that that would be the same formula just when simplified. And I said the great thing about recognizing an arithmetic sequence that we're adding up the terms is we have this formula for its partial sum. So if I know the first term, which we did, the last term we were considering, which we found, and the order of the last term, which it was the 12th, then you can find the entire sum, and it really quickens the problem. Take a moment to pause the video and read through the example, underline some of the key ideas. So here we have that a man earns $100 in the first week of June. Each week after that, he earns $12.50 more. And what we see this is a common difference, right? Every week he gets $12.50 more. That makes us think of an arithmetic sequence. After 12 weeks of doing this, how much has he earned? Well, this is equal to the idea of the sum from the first 12 weeks, from n equals 1 to 12, of the arithmetic sequence where we've got the starting salary of $100, plus we've got our n minus 1 for the arithmetic sequence, times the common difference of $12.50. Because this describes the relationship between each week's payment. During the first week, if you plug n equals 1, this is 1 minus 1 is 0. That whole term goes away and he just makes $100. But then during the second week, 2 minus 1 is 1, so he makes $100 plus $12.50, and it continues like that for the 12 weeks. So this problem is asking us to sum up the first 12 terms of an arithmetic sequence, and we know is equal to n times the first term plus the last term that we're considering, all divided by 2. And in this case, our first term, we're considering the first 12 weeks, so n is 12. Our first term is $100, and we do need to find how much money he's making in the 12th week, so we'd say a sub 12 is 100 plus 12 minus 1 times $12.50. That's equal to $100 plus 11 times $12.50. And we'd see that in the 12th week, he is making $237.50. So we would add that to the first week's salary, divide that by 2, and we get the overall salary for the 12 weeks of work for this particular job is $2,225. Now, so far we've been talking about how do we find the partial sum of arithmetic sequences, and next we're going to see how do we find partial sums of geometric sequences. Now remember, for geometric sequences, they differ by a constant multiple, and a geometric series is just the idea of adding all the terms in the sequence together. So a geometric series is the idea of summing up all the terms in the geometric sequence up to a certain point, and the formula for the first n terms of them is the partial sum s sub n, but in this case we know this is dealing with the geometric series because we've got our common ratio, is equal to the first term times 1 minus the common ratio to the nth power, all divided by 1 minus r. So this will be an important formula to help us identify the partial sums for geometric sequences. So we're going to use this formula to find the 11th partial sum, that's how we would phrase this, of the following expression. Now let's just verify why this is geometric. Think 8 times what gives you negative 4, that would be negative 1/2. Negative 4 times negative 1/2 would indeed give us 2, so we could say this is a geometric. We've got the first term is 8, the common ratio seems to be negative 1/2. So we know the 11th partial sum would follow the formula. S sub 11 is the first term of 8 times 1 minus the common ratio. Now, particularly when your common ratio has more than one term or is negative, keep it all in parentheses so that it's evaluated correctly, to the 11th power, all divided by 1 minus the common ratio. And that's going to be equal to, now as we're calculating this, we do want to keep in mind that this should be probably pretty small because the common ratio of a 0.5 is just going to make things smaller and smaller. So for instance, the next term would be a -1, and then a positive 0.5, and then a negative 0.25, and so on. So we'll carefully type this into our calculator, and we would get in the end, this would be the partial sum of the first 11 terms of this series. Now in our next example, we see our summation notation. So we're saying the sum starts when k is 1, continues to when k is 6, so that's going to be through 1, 2, 3, 4, 5, 6, adding all those terms together. So if we wanted to, we could just evaluate this. This is 3 times 2 to the first, plus 3 times 2 to the second. It's not too big of a sum, so we could just write it out. We know we stop when k gets to 6. Simplifying this, you could add it all together, that would be your value. But another thing we could do is we could recognize, hey, this looks exactly like a geometric sequence. This is the nth term, I guess I'll say in here the kth term, is the first value times 2. Now the only thing is, normally it should be k minus 1, which we don't see here. The exponents are slightly off. So what that means is we really need to evaluate what is our first term. In this case, it's 6. And then the next one is 3 times 4, which is 12. 3 times 8, which is 24. 3 times 16, which is 48. And we can see that this looks exactly like a geometric sequence, except the exponent's not minus 1. So we can't use the exact same formula. In this case, we know that our a1, since our exponent is off, would be 6. We just found that by evaluating in the formula. The common difference is a multiplier of 2 each time, which is the same from there. That's our common ratio. So the general formula for this is a sub k is 6 times 2 to the n minus 1. And these are the exact same formula piece by piece. It just depends on whether you want your exponent to be k or k minus 1. So don't worry about how to get from here to here, although we could using exponent rules. The main idea is you write out the first pieces, you recognize this is a geometric sequence, you find the first term, you find the common ratio, then this is the given formula. Once we know the formula, then we know the nth partial sum is always equal to the first term times 1 minus the common ratio to the nth power, close the parentheses, all divided by 1 minus r. Now we are going up to the sixth term, so that's our highest power, that's our k. So the sum of the first 6 terms is going to be equal to the first term 6 times 1 minus the common ratio to the, okay, in this case we're adding up the first 6, so that's what goes there, all divided by 1 minus the common ratio. And I do want to point out this 6 is different than this 6. This 6 comes from the first term, whereas this 6 comes from the fact that we're summing up the first 6 of these. So that is one thing to keep in mind, the difference there. So we're going to evaluate this in our calculator, and we would get the sum of the first 6 terms is 378. A good place to start when you're doing these problems is to always write out the first few terms, see if you can recognize the pattern. If it's geometric, use the geometric partial sum formula. If it's arithmetic, use the arithmetic partial sum formula. We're asked to find the partial sum of the first 20 terms, so that's nice. They've told us the first 20 terms there. And the series is defined as this. So let's see, what kind of series is it? It's not arithmetic because at first the common difference is minus 500, then it's minus 250. But I think it would be geometric because the first is multiplying by 1/2. That pattern holds there. So it looks to be geometric with the first term equals 1,000. The common ratio equals 1/2. Then we have a formula that the sum of the first n terms of a geometric formula is the first term times 1 minus r to that nth power, all divided by 1 minus r. So in this case, they even told us we're going to 20. So we're looking for the sum of the first 20 terms is the first term, 1,000, times 1 minus our common ratio of 0.5 to the 20th, all divided by 1 minus 0.5. Carefully evaluate this in our calculator, and we would get, and that would give us about 1,999.998 when rounded. Now our next example has, at a new job, an employee's starting salary is $26,750. Let's suppose he receives an annual raise of 1.6%. We're asked to find his total earnings at the end of 5 years. So notice this is not the salary at the end of 5 years, but the total earning of 5 years' work. Now, whenever we're asked to find these total earnings, what we could do is we could just write it out basically: the salary at year 1 plus the salary at year 2 plus the salary at year 3 plus the salary at year 4 plus the salary at year 5. That would work completely fine. But that would be a little bit lengthy, so we might be more efficient if we try to understand how is this problem behaving, and do we have any formulas that would help us. Now the idea of a constant percentage raise is the idea of some kind of constant multiple. This is growing as a geometric series. So this raise, if you get a raise of 1.16, the way you would figure out what constant multiple is that is you would turn 1.16 to a decimal, which is 0.016. I move the decimal place over twice. And then you would say with the raise, you keep the first salary 100%, that's a 1, but then you add that extra percentage to it. So it's the same of having this as the constant ratio. And we can check that. At year 1, we are expecting this amount as a salary. But at year 2, by this idea, we should be able to take this constant multiple and multiply it by the current year's salary, and we'd expect to get 27,178. And that's the exact same idea as if we did the raise, because we know whenever you're growing by a certain percentage, that could be the idea of the initial amount times 1 plus the percentage growth rate as a decimal times the number of years that you're growing by, and that fits this idea. So to calculate the salary at year 3, what we would do is we would just multiply the year 2 salary by the constant multiple of 1.6 percentage growth, and we would expect 27,612 and 848. And we know we could keep doing this for year 4 and year 5 and add everything together. That works fine. Another way to do this problem is to recognize that this is a geometric series, because we have the same idea. Constant percentage growth is the same as constant multiple growth, and we talk through how you find that constant multiple, where the first term is given to us, and we can find the common ratio. And we're looking for the sum of the first 5 years. So the partial sum of a geometric series is always the first term times 1 minus the common ratio raised to how many years we're looking at, in this case 5, all divided by 1 minus the common ratio. So feel free to go through and add it up piece by piece together, or use this formula once we recognize it's a geometric series. In either case, we would get our final answer to the sum of the first 5 years' salary to be rounded to 2 decimal places, and we would get the sum of those 5 years working would accrue $138,099.03 when rounded. One key tip: if you're typing all this into the calculator, be sure to use parentheses, and then you say divided by all of the bottom in parentheses, and the exponent of 5 is only going to this term, not to 1 minus 1.016. So you'd want to type in parentheses 26750 times open parentheses 1 minus open parentheses 1.016 close parentheses to the fifth, close the parentheses that show this multiplier, and then close the parentheses for the fact that this is at the top, all divided by parentheses 1 minus 1.016 close parentheses. And if you type it in carefully, then your calculator should give you the correct answer. Now, so far we've looked at how to add up a finite amount of terms in a sequence or a finite series. In these last examples, we're going to look at what does it mean to add up infinitely many terms. And we can only do so for infinite geometric series. That's the only one that we really have a formula for right now. So if you recognize that you're adding up a geometric series, and instead of stopping at some point you see this dot dot dot, that means it continues out forever and ever and ever. That's the idea of adding up infinitely many things along that pattern. We see the dot dot dot. In that case, the formula is this: because we're not doing the partial sum up to n, we're doing the entire series added together. So literally adding up infinitely many things. But because geometric series behave so nicely, then if our common ratio is between, this should be a -1 and 1, we've got this formula for the sum of the entire series. So it says find the sum if it exists for the following. The reason it says if it exists is because if r is greater than 1, it does not exist. It's an infinitely large sum. So we first have to make sure, is r less than 1 and greater than -1? So between -1 and 1. As we look at this first example, do we see that it's subtracting 1 each time? So this is an arithmetic sequence. The common difference is -1, and since this is dot dot dot, the next term would be 6, then 5, then 4, then 3, then 2, then 1, then 0, then -1, -2, -3. It would continue out to be -100, -1,000, -5 billion, -6 trillion. It would just keep going on and on and on forever. And we can imagine at that point your number is getting negative more and more and more. It's going to the idea of negative infinity. It's not reaching a value because you keep adding more and more negative terms, but it's getting more and more negative. So for arithmetic series, their infinite sum does not exist because it's getting infinitely large. In this case, to the negative. So I guess infinitely small, smaller and smaller and smaller, larger and larger negative number. Now in our next example, I first think, is this arithmetic? It seems like we drop almost like 150, but then the next one we drop less than 60. So it's definitely not arithmetic. This is one of those cases where if it's geometric, it's not as obvious. This isn't clear multiples. So you can always calculate it by taking the later term and dividing it by the previous term. we'll need to get our calculators for this, so that would be exactly 0.4. Let's see if that pattern holds. Take the next one, later, divide previous. Always have to do later divided by previous. Also it's 0.4. So even though it wasn't as visually clear, these are following the multiples of 0.4 each time. That means we're dealing with a geometric series where r is equal to 0.4, which is definitely less than 1, so we've met the criteria there. And since we've got the dot dot dot, it's continuing forever, so infinitely, there's no end in sight or ever, so the sum in this case is the first term, 248.6, divided by 1 minus the common ratio of 0.4. Carefully type this into our calculator and we would get 414.33 when rounded to 2 decimals. So if you're looking at a series that goes on based on the dot dot dots at the end that tells us to keep going on forever, you first need to check, is it arithmetic or geometric? If it's arithmetic, the sum does not exist because it's either getting infinitely large or infinitely small. But if it's geometric, then in that case, if the common ratio is between -1 and 1, if that is the case, then we can use this formula to find the sum of all the terms in the series added together.